Welcome to today's Explainer. I am absolutely thrilled you're here. Let's just dive right in, shall we? Today, we're opening up the doors to our virtual lab to investigate a massive, and I mean massive, bottleneck in our field. We're talking about how to train gigantic AI models using standard, everyday consumer hardware. So, think of this as my comprehensive lab report, where we'll detail exactly how researchers are finally breaking through these massive computational walls. 780 gigabytes. Just let that number sink in for a second. That is the jaw-dropping amount of GPU memory you'd need to fully fine-tune a 65 billion parameter model, like Llama, if you're using standard 16-bit methods. For most of us independent researchers, developers, or even, smaller startups, this requirement is a literal brick wall. It stops AI experimentation dead in its tracks. You'd essentially need a highly expensive, enterprise-grade server farm just to pull this off. But thanks to some really brilliant recent breakthroughs, we can now completely bypass this barrier. So here's our syllabus for today's lab report. First, we're tackling the GPU memory bottleneck. Then, we'll introduce LORA, or low-rank adaptation. Third, the QLORA quantization upgrade. Fourth, we'll look at the actual lab results to test the math. And finally, we'll wrap up with real-world AI fine-tuning. All right, let's kick things off with part one, the GPU memory bottleneck. Okay, so normally if you want to teach a pre-trained AI model a brand new, highly specific skill, let's say summarizing dense legal documents, the traditional go-to approach is full fine-tuning. And that means you are updating every single parameter of that pre-trained neural network during training. The entire network is participating in the gradient computations and parameter updates. Now, conceptually, super straightforward, but computationally, it is an absolute nightmare. Because when you're doing full fine-tuning, you aren't just storing the massive model itself in memory. The optimizer also has to store all these additional momentum and variance states, which essentially doubles or even triples your memory demands. In recent benchmark experiments by my peers like Congo Ni at NYU, they found that even for relatively compact models, say in the 1 to 3 billion parameter range, you hit that memory wall incredibly fast. In fact, attempting full fine-tuning on a 3 billion parameter model using a standard 24 gigabyte RTX 4090 GPU, it just resulted in a catastrophic out-of-memory error. It simply couldn't be done. Which brings us to part two, enter LORA, low-rank adaptation. LORA stands for low-rank adaptation, and it is a total game changer. Instead of updating the entire model, LORA completely freezes the massive pre-trained base model weights. Then it injects these small, trainable rank decomposition matrices into specific layers. Think of it like this. If the base AI model is this massive, heavy, incredibly expensive printed encyclopedia, traditional fine-tuning is like trying to reprint the entire encyclopedia just to update a few paragraphs. LORA, on the other hand, is like writing your new facts on a few sticky notes and just placing them on specific pages. You leave the original book completely untouched. The core math behind this magic actually relies on some pretty simple linear algebra. During fine-tuning, we're trying to find the weight changes, which we represent here as delta W. But instead of calculating that absolutely massive matrix, LORA decomposes that weight change matrix into two much smaller matrices, A and B. When you multiply A and B together, they approximate the exact changes you need, and by doing this, we can reduce the number of trainable parameters by up to 10,000 times. No, seriously, 10,000 times. Looking at this architectural breakdown straight from the source research, check out full fine-tuning on the left. You see that huge 32-bit optimizer state box hovering over the base model? Yeah, that's exactly what causes your GPU to crash and run out of memory. Now, look at the middle column for LORA. The base model is entirely frozen. You can see that indicated by the green arrows, and we only have to worry about these tiny adapter matrices and a vastly smaller optimizer state. But take a look at that third column, because we can actually push this even further. Notice how the base model suddenly says 4-bit transformer? Well, that teases our next major breakthrough. And that is part three, QLORA, the quantization upgrade. So QLORA expands on our sticky note concept by combining it with extreme compression. As researchers, we introduce three key innovations to make this happen. First up is 4-bit normal float. We basically take the massive 16-bit or 32-bit base model weights and squish them all the way down into just 4 bits, mathematically optimizing it so absolutely no crucial information is lost. Second is double quantization. This literally quantizes the quantization constants to save even more space. We're talking about saving roughly 3 gigabytes on a 65 billion parameter model just from that. And third, we use paged optimizers. These intelligently shift memory back and forth between the GPU and your computer's regular CPU RAM to prevent any sudden memory spikes from crashing your training session.
Let's move on to Part 4, Lab Results. It's time to actually test the math.
When we compare the GPU memory requirements across these different methods, the breakthrough becomes undeniably obvious. Just look at the full fine-tuning row. That smaller 1.6 billion parameter model ate up over 15 gigabytes of VRAM. And for the 3 billion parameter model, out of memory, dead on arrival for a standard RTX 4090 GPU. But then, look at the bottom row. With QLORA, that exact same 3 billion parameter model suddenly only requires 2.54 gigabytes of memory. That is a total game changer. QLORA was quite literally the only method that allowed our colleagues to train the larger model without a catastrophic hardware failure. But I know what you're thinking. What about the actual performance, right? Well, in this evaluation loss comparison, where a lower loss means the model is performing better and is much more confident, check out the far right. For the Zephyr 3B model, the QLORA bar is significantly lower than the standard LORA bar right next to it. And this brings us to the absolutely critical takeaway from our lab evaluations. QLORA isn't just lighter on memory. It actually achieved better, more stable generalization than standard LORA in these trials. The quantization noise didn't ruin the performance at all. In fact, when we paired it with the low-rank adapters, it provided the most stable optimization path possible. It's the ultimate win-win. You get the highest efficiency combined with the absolute best end result.
Finally, let's wrap up with Part 5, Real-World AI Fine-Tuning.
This matrix right here perfectly summarizes the revolution we've achieved. We have taken fine-tuning from a grueling process requiring 24 to 48 gigabytes of memory and modifying 100% of the parameters, all the way down to QLORA, which needs just 4 to 8 gigabytes of VRAM while changing a fraction of a percent of the parameters. We've literally moved AI development from the expensive corporate server farm straight down to the hardware you might find in a teenager's gaming PC. And because of this, the real-world applications are just exploding right now. Thanks to LORA and QLORA, developers are deploying highly customized chatbots directly onto edge devices, like mobile phones. In computer vision, researchers integrated LORA into human activity recognition systems and achieved a massive 32% boost in accuracy while updating just 0.5% of the model's parameters. That's incredible. And startups, they are drastically reducing their compute costs, easily fine-tuning models for highly specialized legal and medical domains that were previously way out of financial reach. Just take this actual field note shared by a developer on Reddit. They wrote, QLORA let me train a legal document summarizer using only 6 GB of VRAM, something that would have been impossible with full fine-tuning. I mean, that perfectly cements the sheer democratization of AI that QLORA has unleashed. It takes the power that used to belong exclusively to tech giants and hands it directly to individual developers. We've seen how elegant math, freezing base weights, decomposing matrices, and squishing data down to 4 bits can completely dismantle the hardware barriers that were holding back AI research. The tools are now directly in your hands, ready to run on the hardware sitting on your desk right now. So I want to review with this provocative thought. Now that the hardware barrier is gone, what custom model will you build in your lab today? Thank you so much for joining me for this explainer. Keep researching and keep building.